Hello everyone and welcome back. In this video we're going to be revisiting a very common topic that is seen in all realms of statistics, and that is the concept of an outlier. We're going to be discussing what an outlier is and some common ways that people use to detect outliers. Now the first thing that we need to do is of course define what an outlier is. So I think a reasonable definition of an outlier is a data point that differs significantly from other observations. Now this definition isn't perfect, but I think it gets the important point across about what an outlier represents. But the thing that we really need to explore is, what does it mean to differ significantly, and what if these other observations are not exactly reliable? So the first thing that we need to do is this. So we need to first define a distribution to compare our data points to. And then we can see if those data points that we obtain vary significantly from this distribution that we're sort of using as our point estimate for the population. So let's just do a basic guiding example. Let us suppose that our population P is associated to a normal distribution with some mean mu and some variance sigma squared. So this distribution here, this normal distribution, is the claimed distribution of P. And let's assume we call this claimed distribution of P, let's call it phi sub 0x. So it's sort of like a null hypothesis claim. And of course you can, conduct a hypothesis for this distribution by doing, say, a chi-square goodness of fit test or a Kolmogorov-Smirnov test or some of the other different types of tests that one can use to test populations. So let's look at a couple samples from this population and see if it appears that they are actually coming from this distribution, and let's see if we can classify some outliers for those particular samples. So let's assume our first sample has this type of distribution. Let's assume this is the x-axis for the variables in this particular population. Let's assume that this is mu, and let's assume that this is mu minus 3 sigma, and this is mu plus 3 sigma. We know from the empirical rule that about 99.6% of the data points should lie between 3 standard deviations from the mean. So let's assume that our data set points are sort of clustered around the mean, so these x's are sort of like our data points. And of course they're going to scatter as you move along. And then let's assume we have this point here. Let's assume we have this point here. So if we decide that the population is truly normally distributed, one can ask the following questions. So the first 2 points that you probably want to look at are the extreme, maximum, and minimum values, and ask the question, are these data points outliers? And of course, if you decide that they are outliers, then you may want to consider possibly other points, maybe that point and that point, because they're close to these 99.96 boundaries. But there are some situations where 3 standard deviations from the mean actually should not be considered as the cutoff. Sometimes 5 standard deviations from the mean is significant to some studies. Therefore, if you use 5 standard deviations, it's possible that these 2 points are within those boundaries and then hence are not outliers. But of course, that's a very, common example. Maybe you would and maybe you would not. Now, another interesting example is this. Let's assume again that this is the same x-axis. Let's actually move these purple cutoff points a little bit. Let's actually put mu there. Let's put mu minus 3 sigma and mu plus 3 sigma there. So it's the same exact values because we're still assuming that these samples are coming from this normal population. But now let's collect another sample. Let's assume we get a point there, and a point there, and a point there, and we get a bunch of data points here. A bunch of data points there. So then the natural question, if we were to use these same cutoff values, mu plus or minus 3 sigma as our cutoff values for determining that some points are or are not outliers, then we need to stay consistent with those, right? So every point outside of these boundaries would then be considered outliers. So again, all of these points here, which appears to be most of our data set, would be considered outliers. So again, you need to ask the same exact question. Are all of these outliers? or not. Right, and that's sort of the main questions that we're going to sort of explore in this, because both of these samples are highly possible in the sense of random sampling from a population, right? So how do you decide which are and which are not outliers? So there's definitely some error, type 1 and type 2 errors to sort of keep in mind here. So let's sketch out a basic strategy that we will explore, at least in this discussion. So the first thing that we need to do, step 1, is to decide on a comparison distribution or a hypothesized distribution for p. So that is this function phi sub 0x. Then, step 2, we need to decide on thresholds of or on the domain of our function phi 0. That is what our cutoff's going to be. So in this particular example that I was talking about, mu plus or minus 3 sigma would be our threshold cutoffs for outlier detection. And then once we decide our thresholds, then step 3 will be classify points as outliers of our distribution phi and not outliers of phi. Now notice I'm changing the notation a bit here. So phi 0 is the claimed distribution. Phi is the distribution that this phi 0 is trying to approximate. So this is the true distribution. This is the, the null hypothesis, the claimed distribution of the population, because technically we'll never know the exact distribution phi of a distribution, but once we classify points as outliers or not outliers, then technically we are still referencing the distribution that we're trying to model. So that's a basic strategy. So let's look at an actual example and see how we would construct these threshold values based upon our preferences for cutoffs and area distributions for our data set. So as our first example, let us assume that the population is associated to a normal distribution with a mean of 0 and a variance of 1. Some people usually refer to this distribution as the standard normal distribution. This is the distribution that we use to calculate, for example, the z-critical values for, say, confidence intervals and p-values for, say, the proportions and sometimes even the mean. So let's assume that we want to construct the quantiles for this distribution. The quantiles are going to be very, very useful because they're not as skewed by outliers as, say, for example, the mean or the standard deviation or other different types of metrics. So what is a quantile? Let's just sort of review what it means to be a quantile. So here's going to be our normal distribution. Our quartile splits our data set up into 4 regions, each of the same exact size. So the median, sometimes called the center quartile, is going to be equal to 0 by definition of the standard normal distribution, because it should be symmetric about the mean, which is, of course, the median if it truly is symmetric. Now we're going to be looking for the inner quartiles, which is going to be Q1 and Q3. So between Q1 and Q3 should lie 50% of the data. So 50% of the data should be lying in that particular category, where 25% of the data is in between Q1 and Q2, and another 25% is in between Q2 and Q3. With that being said, that also implies that there's going to be 25% in the lower tail, and that's also going to imply that there's going to be 25% in the upper tail, right? And then we're going to start deciding what Q0 and Q4 are going to be, and that's what we're going to sort of use as our thresholdings for outlier detection. Right? So if we go ahead and calculate what these inner quartiles are going to be, for example, how would we do that? Well, notice that Q1 is the 25th percentile of this distribution, N0, 1, and Q3, remember, is going to be the 75th percentile of N0, 1. And you should know already how to calculate those numbers, and once you actually go ahead and do so, you can find that Q1 is approximately equal to negative 0.6745. So that's the z-score associated to Q1. And if you want to find Q3, well, you actually should know what that is equal to because this is a symmetric distribution. Q3 should just be the positive of that. So it's going to be positive 0.6745 approximately. So what is the interquartile range for a normally distributed data set? In particular, one that is standard normally distributed. So that's just the distance between the interquartiles. So IQR, which is always equal to Q3 minus Q1, which is technically 2 times the positive one. So that can come out to 1.34902 for decimal places. Now, technically, if you want to make this distribution a general normal distribution with any particular mean and any particular variance, is there a general formula for the first and third quartile and hence the interquartile range? And definitely there is, and let me just sort of entertain that idea. So what if our population P is a normal distribution with an arbitrary mean and variance sigma squared? So in some sense, these are z-scores for the interquartiles. So we can convert back to a standard domain via the z-score transformation. So one can find that Q1 is going to be approximately equal to mu minus 0.6745 sigma. So that is the z-score associated to Q1. And then Q3 is going to be approximately equal to mu plus 0.6745 times sigma. So that are our formulas for the first and third interquartiles for a general normal distribution. So now let's go back to our question about outliers. So question, what are good, that's a subjective phrase of course, good cutoff values, and let's call these cutoff values XL and XR, where these are our lower and right boundaries for our outliers, right? So let's just sort of go back to what we were talking about before. So we know that the area under the curve of a standard normal distribution, let's call that standard normal distribution f of z, we know that this is approximately equal to 0.9973. So you need to ask yourself, 99.73%, is this close enough? Is this close enough to 1 for you in particular? If the answer is yes, then we can define -3 and 3 as the lower and upper cutoff values for outliers. So if we sample from a standard normal distribution and we get a value of -3.8 or 5.2, we can classify them as outliers because they are beyond our cutoff values XL and XR, because 99.73% covers most, quote unquote, of the data set, at least with respect to our requirements. So if that is the case, that means what? So if yes, then we're going to be defining XL to be equal to -3 and XR to be equal to +3. So remember, when we first talked about interquartile ranges and outlier detection intervals, we had a nice little structure for that. So we had an interval I, which was defined to be equal to Q1 minus C times the interquartile range, and Q3 plus C times the interquartile range, where this C was a threshold constant. Right? And the guiding question is, well, what exactly is this constant equal to? So we've actually made this into a nicer looking interval. This is actually XL and XR in disguise. So let's see what this threshold constant C should be if we're assuming that our data is normally distributed and -3 and 3 are going to be our cutoff values. So what will be our interquartile range threshold constant value? So let's just set these things equal to each other. So Q1 minus CIQR and XL should be equal to each other, right? So Q1 minus C times the interquartile range must be equal to XL. So Q1, that's always going to be the same. We know what that is. IQR, we always know what that is regardless of the distribution. In particular, our standard normal distribution, we know its value. This value we choose, and that means if we choose that and these other two variables are known to us, that means we should be able to find the C value. So let's just solve this equation for C, and that shouldn't be too hard. So C is going to be equal to Q1 minus XL divided by the interquartile range. So that's going to be equal to approximately negative 0.6745, so that's the Q1 approximation, minus negative 3, all over the interquartile range, which is twice that positive Q1 value, so it's 1.3490. Keep in mind the interquartile range is always positive, so that should be a good thing. And XL should be less than Q1. So if those things are equal to each other, you're going to have that's approximately equal to 1.7239. So this is what we refer to as our threshold constant. Now, if you've been following statistics along with me for a while, this number should be familiar to you. Because back in the day when we were just, creating intervals to detect outliers, I mentioned that sometimes we choose a threshold constant of about 1.7, 1.5, but that's based on some assumptions that we'll get to later. And now I've proven to you that this number is actually based on a normal distribution. But if the distribution is not normally distributed, then of course this number actually isn't going to accurately detect your outliers. Now let's sort of explore this a little bit more, because maybe your answer to this other question before, is this close enough to 1 for you? What if that answer is no? So if that's not close enough to 1 for you, that means we need to go a little bit more farther out into the tails of a distribution. So what if we want our XL and XR value to be equal to, say, plus or minus 5. So if that is our plus or minus 5, you should be able to follow the same exact procedures and see that C is approximately equal to 3.2065, using the same exact thing as we discussed before. So you would choose this threshold constant value provided that the integral from minus 5 to 5 of the standard normal distribution is close enough to 1. And you should be able to find that that's going to be approximately equal to 0.1234556, so that's 6 nines, followed by 427. So if this is close enough to 1 for you, and a lot of people use 5 standard deviations from the mean as a nice little basis, that means your thresholding constant would be equal to approximately 3.2. In the case that you believe that the distribution you're sampling from actually is not symmetric, then you can actually let the threshold values be non-equal to each other, or your outlier detection interval I to be asymmetric. Right, so this is going to be an asymmetric outlier detection interval, right? So that means the CL and the CR are not necessarily going to be equal to each other. So to demonstrate how you can sort of obtain these values, I'm going to be using the beta distribution to sort of create a skewed distribution that we can actually easily analytically calculate each of these things. So in case you aren't already familiar with the beta distribution is actually very interesting and has a lot of applications in Bayesian statistics, which we'll talk about later. But you can actually get a lot of interesting shapes about a distribution via the beta distribution, and it can sort of serve as a nice little experimental distribution to play with. So that's going to be equal to gamma of alpha plus beta divided by gamma alpha, gamma beta, times x to the alpha minus 1 times 1 minus x to the beta minus 1. So that's what we call the beta distribution. So just a basic couple properties about this function. First off, the domain of this function is going to be the interval 0 to 1. You can scale that outwards if you wish, but that's the basis interval. And these alpha values technically can be any positive real number. So usually people let alpha and beta be any positive real number. Some people choose bigger than 1, but it's not necessarily the case. And if you change these values of alpha and beta, you're actually going to get a lot of different types of shapes, which is actually pretty interesting. So if we want to create a asymmetric or a skewed distribution via the beta distribution to sort of play with, then we can let alpha and beta be unequal to each other. So suppose alpha is, let's say, 3.9, and let's beta be equal to 1.3. And there's lots of theoretical things that goes along with this, but let's just assume that everything is beautiful and wonderful. So let's assume that this again is 0, 1, so this is our interval, and the beta distribution is going to look something like that. Actually, not that heavily skewed, but sort of looks like that. Actually, I think it's easier to draw from that side, right? So it's definitely not a skewed distribution because this would be 1/2, right? So it's definitely skewed to the left. Now, if you're familiar with Desmos, you should be able to easily verify these next couple statements that I have, but you should be able to find that the mean of this distribution is equal to 0.75, and the median of this distribution is equal to approximately 0.7834. So since the median is greater than the mean, then we have evidence to believe that it is skewed to the left, in case it's not obvious from the graph. So since it is a skewed distribution, then you might be tempted to make an asymmetric outlier detection interval. So let's see if we can construct, for example, the quartiles, the interquartile ranges, decide a nice cutoff value, and then determine what our constants should be equal to. So let's draw our beta distribution here, just temporarily. So let's assume that this is our beta distribution. Let's assume that that is 0 and that is 1. So the area under this curve is equal to 1. That makes it a PDF. So Q1 is going to be somewhere here. And let's assume that the median is somewhere here. All right, so the median is there. And Q3 is probably going to be somewhere over there. Okay, so why do I focus on the median here? Remember, the median sort of cuts this distribution in half, 50% of it to the left and 50% of it to the right, because the median, remember, is Q2, right? So that means this area here, that should be 25%. This area here should be 25%. Okay, so if you know how to solve these backwards things, these backwards integral equations via, say, Desmos or some other software, you should be able to find that Q1 is approximately equal to 0.6416 and Q3 is approximately to 0.8895, right? So how do you get that? You can use percentile calculators. That is the 25th percentile, and that is the 75th percentile of this particular beta distribution. And of course, you should be able to find the median, Q2, that's approximately equal to 0.7834. Right? So those are your inner quartiles and center quartiles. Now let us determine how far is far from the middle. Right? So let's draw our distribution again. Let's assume that's the same exact picture. It doesn't look like it, but let's assume that is the case. So let's again let that be Q1 and Q3. And we know that the area between them is equal to 50%. And how much do we want to allow in the tails? Like, how far is too far? So we know that the entire area to the left of Q1 is 25%, right? So let's go all the way out to some point close to 0 such that this area is 24.99%, right? If that's 24.99%, let's also do area over here of the same exact value, 24.99%, because we know there's 25% area there to play with, but let's sort of cut it off at 24.99%. That means there's 0.01% left in these little tails. This little tail here and this little tail here. That means this area is going to be 0.005, and that area there is also 0.005. The only difference is these numbers here, that value XL, which is close to 0, and this number there, XR, which is close to 1, are not the same exact distances from those boundaries. So these are asymmetric intervals. Technically, this XL probably should be a little bit more farther up in the picture, but hopefully you get the hint. So let's see if we can find out what these are. So how would we go about that? So we know that XL is going to be equal to Q1 minus the lower boundary of the interquartile range. So we know what the interquartile range is, we know what Q1 is, and we should be able to find XL, right? So how are we going to find XL? Well, firstly, we can find the interquartile range by subtracting Q3 and Q1. So you can find that the interquartile range is going to be equal to Q3 minus Q1, which is going to be approximately 0.2479. So once you have the interquartile range, then you should be able to find XL. XL can be found to be approximately 0.2259. Similarly, XR, which is equal to Q3 plus CR, times IQR, that's going to be approximately equal to 0.9952. So how am I constructing these numbers 0.2259 and 0.9952? Because XL is the 0.005 percentile, and this is going to be the 99.5th percentile. So 0.995 percentile, right? And those are easily constructed from the actual theoretical distribution. So once you have your XL and your XR, then you can find your threshold constants CL and CR. So by solving that equation, so subtract both sides by Q1, divide both sides by negative IQR, and that's going to give you CL is approximately equal to 1.671, and CR approximately 0.4264. Notice how different that these threshold constants are, right? So they're definitely not equal to, they're definitely asymmetric based upon our particular symmetry or asymmetry. So notice that our distribution is skewed to the left. So what is the relationship between the left and right threshold values? So we can propose or conjecture the following observations. So if our proposed distribution is skewed to the left, then the left threshold constant typically is going to be greater than the right threshold constant. If our distribution that we're sampling from, or our proposed, is skewed to the right, then CL should be less than CR. And if our distribution is symmetric, or close to symmetric, so the mean and the median are close to each other, then CL and CR should be equal to each other or really close to each other. Now, are you going to be sampling from a beta distribution? Probably not, but once you do have a proposed distribution in front of you, you can follow these same exact steps in order to construct what your CL and your CR should be equal to. So before we start classifying outliers, definitely having a good grasp of the distribution that we're sampling from definitely is a must. So every time you start outlier detection, you definitely should start by doing a goodness of fit test. So since it is a test, there is a potential of making some errors. For example, the null hypothesis is that the true distribution of the population is equal to the distribution that you say it is. For example, you say that it's normal distribution, that would be phi 0. But it's possible that phi actually is not normal. So the null or the alternative hypothesis is that the distribution actually is not equal to that distribution, for example, a normal. So there are definitely going to be some errors that you could make in this process. For example, the null hypothesis could be true, that it actually is normal, or the null hypothesis could be false, that the distribution actually not is normal. And of course, we have a couple conclusions, either rejecting that claim or failing to reject that claim. Right? So of course, which is the error in this little square? So rejecting something that is true definitely is an error, and failing to reject something that is false definitely is an error. So we know that alpha is the type 1 error, beta is the type 2 error, and of course we have the power of the test and our level of confidence here in green. But the main thing that we need to focus on is these type 1 and type 2 errors. But notice that this square is only for the distribution. right? So even though the distribution might be true or false, then we need to go to the next step and start classifying outliers. All right, so let us assume that the distribution actually is normal and we fail to reject it, right? So failing to reject the null hypothesis when the null hypothesis is true. That is the most ideal case usually in the hypothesis testing spectrum. So once you are able to do that, hopefully, then comes stage 2 of the outlier detection process. So the next null hypothesis that you need to test is that x is an outlier of the distribution of phi. And of course, you would test that with the two-sided alternative that x is not an outlier of the distribution of phi. Again, we have a similar type 1 and type 2 error again. So we have the possibility of rejection and the failure to rejecting the null hypothesis. And then we have that the null hypothesis is true and the null hypothesis is false. We still have a type 1 and type 2 error here. So there's our type 1, that's our type 2, there's our C, and there's our pi. So these are going to be our issues. But notice this is a completely different test. So what is this? So this is the claim that a point actually is an outlier. So if a point actually is an outlier, rejecting that claim is showing that the point actually not is an outlier. Some people will switch these null and alternative hypothesis. That is perfectly okay. That is still equivalent. Now, failing to reject the null hypothesis when the null hypothesis is true, that is a good thing. So when a point is claimed to be an outlier and it actually is, that is great. That means we're probably going to be getting rid of some points that actually don't belong there. Now, what is this next situation here? So failing to reject the null hypothesis when the null hypothesis is false. So that is our type 2. So the null hypothesis in this case is that a point is an outlier. Now, if the point is an outlier, so if the claim is that it is an outlier and the null hypothesis is false, that means a point actually is not an outlier, right? So if you fail to reject that claim, that's definitely going to be an issue. So this first little box is for distribution, and the second is for outlier classification. Now, it's possible that you get rid of an outlier or you classify a point as an outlier for the wrong reasons, right? Let's actually look at a couple pictures here to sort of see what I mean by that, right? So a little example. So let's assume that this is our mean, this is our left boundary, and this is our right boundary. So if these are our boundaries for outlier detection, that means this point is going to be okay, that point is going to be okay, these points, that's going to be our outlier 1, and let's assume you have another point out here, that's going to be our outlier 2. Now, these points could be wrong, right? These points could be wrong. These could be wrong. But you could change them to be larger, right? For example, if we move these boundaries a little bit outwards, then those points are no longer going to be outliers. Now, another situation that you definitely need to be aware of, right? So let's assume that our mu is there, our XL is there, and our XR is there. And let's assume that we get a bunch of points, for example, here, here, and here. Let's also assume that the distribution for the actual distribution is hanging out over here. So this is the true distribution, right? So our detection interval says that these are not outliers, but actually they are with respect to this distribution, right? So these truly are outliers, but we're actually not going to be describing them as outliers. Then comes this next category. So these are going to be outliers with respect to our distribution and possibly with respect to the actual distribution as well. So these actually are classified as outliers for a good reason by accident, right? These are going to be classified as not outliers because our assessment of the distribution is actually false. Now these points, let's put them in orange, are going to be classified as outliers because they fall outside of the XL and XR boundary, but they actually belong to the actual distribution that we're sampling from, right? So notice that there are a lot of downsides to this process, but again, that's the downside of outlier classification, is because you have to know the distribution you are sampling from, right? So there's definitely two big cases you should be aware of. So case one is the following, that the stars are outliers. So the stars are outliers with respect to a true distribution, and case two is that these points, these stars, are not outliers with respect to this true distribution. So either they are outliers or they are not, and those things are typically independent from our detection intervals. So definitely keep aware of all of these things, because we have two different hypothesis tests going on here. One, the test associated to the distribution, and second, the test associated to the actual classification of these outliers. Now I'm going to introduce a couple hypothesis test strategies that you actually can use so you don't have to guess too much in terms of outlier detection. So the first test that I'm going to introduce is based on the assumption that the population you're sampling from actually is normally distributed. So instead of actually going ahead and choosing your threshold constants or your lower and upper bounds, you can actually perform a hypothesis test, sort of like we did, for example, with the p-values and test statistics for other different types of metrics. So the test that I'm going to introduce you all now is known as the Grubs test. So the Grubs test usually is based on the assumption that typically the minimum of a data set and or the maximum of the data set are outliers, if outliers do exist. Right? Because if they are outliers and we're assuming normally distributed, then the outliers are usually located in the tails. So it's usually the maximum and the minimum. So Grubb's test is only focused on one outlier, not two or more. I'll briefly discuss an extension of the Grubb's test momentarily. So what is the test statistic for the Grubbs test? So the test statistic, which I'm going to represent as G-stat, is defined to be equal to the maximum value minus the mean, divided by the standard deviation. If you know sigma, use sigma, but usually we don't, so we usually use S. That's if you're proposing that the maximum is the outlier, or you can use the minimum. G stat is going to be equal to X min minus X bar all over S. You may see some people reverse these two. They will do X bar minus X min, because usually X bar is greater than X min, so they want that test statistic positive, but it actually doesn't matter, and I'll let you sort of think about why that is the case in just a moment. Right? So now this structure should look relatively familiar, because technically this looks like a t-test statistic, right? It has that same exact structure. So what are we actually hoping for? So if the maximum and or minimum is truly an outlier, then this distance, some people call it the gap, should be significantly large. So what are we looking for? So if our G-stat is significantly positive, or our G-stat is significantly negative, either one is okay, but the positive one applies to this one and the negative applies to that one, then we're going to be rejecting the claim that the point is not an outlier. So we're going to be using the complement for the null hypothesis in this case, right? Because we want to reject the null hypothesis if our test statistic is greater than a critical value, right? So our null hypothesis we're going to be choosing as X is not an outlier of the distribution, with a two-sided alternative that X is an outlier of the distribution. Right? So technically these should be one-sided tests, right? So these are going to be one-sided tests, H tests, on a T(n-2) distribution. And why is it a T distribution? Because we have technically a normal random variable on top, because we're sampling from a normal distribution. That's one of the assumptions of a Grubbs test. And we have a chi-square random variable hanging down on bottom. So that's, of course, going to be a T distribution. Now the G critical value for this. Oh, and again, why is it a one-sided critical value? Because our maximum cannot be both above and below our x bar. It can only be on one side. So our g critical value, I'm not going to prove this, but this is going to be equal to n minus 1 divided by the square root of the sample size times the square root of t critical value squared divided by n minus 2 plus the t critical value squared. Right? Now, keep in mind, notice that the t value is squared here. So as long as it's positive or negative but of the same size, you're going to have the same exact g critical value. Now you should understand why it doesn't matter if you do x min minus x bar or x bar minus x min, because when you square them, they actually have the same exact value. Right? So that square definitely is useful, so that's why it doesn't really matter here. So let's actually do a little numerical example sort of to demonstrate what's going on here. So let's assume that S is drawn from a normally distributed population. Let's assume that the sample size is 23, our mean is 76.2, sample standard deviation 5.4, and let's assume that the maximum value is 98.5, and we believe that 98.5 is too far from 76.2. So we want to see, is this an outlier or not? Let's choose an alpha value of 5%, since a lot of people tend to like that number. So where does this F5% sort of tie in here? So we need a critical value in order to calculate our G critical value. So this is going to be a T n minus 2 distribution, where this is going to be my C value, and this is going to be my alpha value. And this number here, that's going to be my T critical value. So what distribution is this? So n is equal to 23, so this is going to be an n, this is going to be an m minus 2, so a T21 distribution, right? Where that is going to be our 95th percentile of our T21 distribution, right? So what is that T critical value going to be? So you should be able to find T critical values by now, but our T critical value is going to be approximately equal to 1.7207. So what is our test statistic? So our test statistic, our G test statistic, is going to be equal to 98.5, that's our maximum, minus the mean, 76.2, all over the standard deviation of 5.4. That's going to be approximately 4.1296. Now, do we compare this to the T critical value? No. You compare it to the G critical value. So our G critical value, remember, uses this T critical value in its calculations. So the G critical value uses this, so sample size minus 1 over square root of sample size, and then the square root of that fraction. Right? So once you calculate your T critical value, plug that into your G critical value formula, and that's going to give you G crit is approximately equal to 1.6126. So our question is 4.12 significantly large? If it is, then we're going to accept the claim or believe or have evidence to believe that that point actually is an outlier. So we're going to be rejecting the claim that it is not an outlier. So how large is large? Larger than 1.6, and 4.1 is definitely larger than that. You can actually construct a p-value associated to this. So p-value is approximately equal to 0.00024, which is technically close to 0. So that's pretty good. So what is our conclusion? So since our test statistic is significantly larger than our G critical value, we're going to be rejecting the null hypothesis because we have evidence to believe that the maximum actually is an outlier. So since the Grubbs test is used only for identifying if one value is an outlier or it's not, what if you suspect many values as being outliers? So what is one way we can do this? So the first approach is what is known as a recursive Grubbs test. This is similar to pairwise comparisons in terms of its structure. So what we're going to be doing is we're going to be defining a set O to be equal to a bunch of points, y1, y2, down to say, let's call it ym, to be the set of all suspected outliers of a data set S, where the size of S is equal to n, and m hopefully is significantly less than n. If you believe that all data points of a sample set are outliers, then you might have some issues with your sampling process. But usually m is strictly less than or significantly less than the sample size. If m is the majority of your data sets, then of course, again, you have some issues with your sample. So the first thing that the recursive Grubbs test does is the following. So step 1. So the null hypothesis is that yk is an outlier. So first we start with k is equal to 1. Right? So y1 is an outlier. Now we need to perform, actually Grubbs test assumes that it's not an outlier, and then we try to prove that it actually is. Right? So we do step 2. We do Grubbs test. So if we fail to reject, if we reject the null hypothesis, so what does rejecting the null hypothesis in Grubb test mean? So if we're rejecting the claim that y is not an outlier, that means we have evidence to believe that it is. So rejecting the null hypothesis will force us to remove yk from our data set S, and failing to reject the null hypothesis means we have evidence to believe that it's not. That means we're going to keep that point inside our data set S. So once you have concluded your Grubbs test for point yk, where k starts at 1, then you're going to cycle back. Then you're going to increase by 1. So increase k by 1, and then go back. Then do it for point 2, point 3, point 4, all the way down to point m. Notice that when you start removing data points, you're working with different data sets at that time. Right? And you continue that for all of your data points. So the downside is what? So remember, there has to be downsides to this. Notice if you start removing things, your standard deviation is probably going to change as well, right? So there are a tower of issues, but there's m potential type 1 and type 2 errors. That's really bad. Same downside or similar downsides to pairwise comparisons. So the good question is there a better alternative? The answer is yes. So the easiest better alternative is known as the Tietjen-Moore test. So the Tietjen-Moore test. So it sort of follows the same exact structure as the recursive Grubbs test, but it does everything in one conclusion, right? So why are we not going to talk about it today? Well, here's the reason why, and maybe you can guess it. So this requires a critical distribution that is based on simulations. Because remember, generally speaking, you don't want to assume anything too strong about the distribution you're sampling from, right? So what they do is they look at your sampling distribution that you're looking at, they collect a bunch of samples, and then they compare, usually it's like 10 million or so samples, to your sample, and then determine, based upon that, does it seem to be that one of your points doesn't match the distributions of these samples that you actually simulated. But that is usually based on a normal distribution, right? So here's a question. What about a non-parametric test? Does there exist a non-parametric test for outlier detection? And sort of think about, what that means, because generally speaking, non-parametric tests are really great because you don't have to assume anything about the distribution. But keep in mind what outliers are. They usually require some distribution to sort of compare them to. So although non-parametric tests for outlier detections may exist, they are very, very sensitive to deviations based upon the theory for which they are built. So that is just a basic introduction to outlier detection and some of the questions and ideas associated to that process. So I hope this helped your understanding of outliers and how you may want to sort of deal with them in the near future, because definitely if you do have outliers in your data set, they can definitely skew your results and definitely change your conclusions far from what they actually should be. So I hope you enjoyed, and I'll see you in the next video. Take care.